Hey, good afternoon.
Afternoon.
So I guess we'll hear any of you or either of you think of questions about like assistantships and graduate programs and stuff after last class.
I have not.
Okay, cool. All good. Just curious. All right, we got 50 seconds. All right, it's 3 o'clock. So now that we got everyone here, I got caught reading my lecture notes. That's on me. Daily quiz is now up. So given the permutation that you see there, and I have it written in cycle notation, what would happen if I give this permutation the value 2? What would the output be? And I'll give you all till 303, unless I get answers in from everyone before that. All right, I got 3 of y'all in. Five, six, three, four, five. And then 2, 3.
How would that be written? Quick question about that. So for like the ones that it does return a value and the other ones when it returns itself, do I need to put down each and every one?
So this is a function with a single input and a single output.
Okay.
Hopefully that will clear that up for you.
Yeah.
I see someone keeps second guessing themselves. But it just turned 303, so I'll give you 10 seconds to type in something or change your answer. All right. I'm going to lock answers. Oh, I'm about to sneeze in 5. Like that was terrible timing. I guess I'll say my sneeze triggered the locking of all the answers. I don't know. Hopefully, you get a chuckle out of that. Uh, so what is the value? Well, we can work through it real quick, but what do you think it is?
3.
4.
That one person saying 3, one person saying 4. Anyone else? I mean, I know I technically see your answers, but
I
Okay.
said 1, but I was so fast, so I think it's 1.
okay. All right. Well, let's figure it out. We kind of have an array of answers there. So let's work through it. When I'm looking at a product of cycles, I'm trying to put an input through it. Which cycles do I start with? Or how do I read the cycles?
Left to
Right to left.
Right.
Right to left, right? So I have one cycle here, which is 1, 2, 3. I have another cycle here, which is 3, 4, 5. And then the last cycle would be 5, 6. And so when I'm passing this input through, I first got to figure out what happens when I pass this input through to the first cycle, 1, 2, 3. But remember, once we identify a particular cycle that we're working with, we then go in and say, okay, now I read this left to right, where it's saying 1 gets changed to 2, 2 gets changed to 3, and then if I need to come right back around, 3 gets changed to 1. So after I go through that first cycle, what is the output going to be? So I give it 2, and it's going to change 2 to what?
3.
3.
And then that input of 3 gets passed into my next cycle, reading from right to left. And then that next cycle, it takes the value 3, and what does it turn it into?
4.
4.
4. And then 4 is going to get passed on to the next cycle. And that cycle 5, 6 is going to take 4 and turn it into what?
4.
Itself.
Yeah. So when I plug 2 into this permutation, what's the outcome?
4.
It'll be 4. Okay, so I think based on the answers that you gave me verbally just now, only one person got that. So mainly what I care about right now is, now do you understand why the answer is 4 and how to go about getting it?
Yep.
Yes.
Cool. Carissa, you can give me a thumbs up if that's the case
Oh,
for you.
sorry, yes.
No, you're good. Normally I would ask, just thumbs up so we don't have to worry about people playing the mute unmute game, but I'm more than happy to hear voices come back at me as well and not just hear myself talk. So thank you all for verbally responding as well. Sinai, how do you feel?
Good.
Cool. All right. So there it is. Okay. I just wanted to make sure y'all see that. See the same screen I'm looking at. All right. So we're going to keep moving on with permutations. And let's just do one more based on that, because I don't think we did this one. What was alpha and beta in this example? Yeah. So let's do one more real quick. Try to solidify some of this cycle notation and understanding how it works with permutations. So we're going to let alpha be, whoops, I didn't mean to zoom in. The cycle 1, 3, the cycle 2, 4, and the cycle 6, 7. And we're going to let beta be the cycle 1, 2, and 3. So what I want us to do is to determine what is alpha beta. So if I compose these two cycles together, what am I going to get? And again, I'm not going to go with the naive, well, I just kind of paste them side by side. It's what is the result? What is the most simplified version that I can come up with of this cycle?
Do you mean
So
like how we could write it?
Mhm.
Oh, okay.
Yep. So first thing I have to identify is what symmetric group am I working in?
S7.
Yeah, S7, because when I go through and look at all of the numbers and all these permutations, the highest one I see is 7. And we said that's what we're always going to assume is our symmetric group or matches with our symmetric group. So we're working in S7, which means I have 7 inputs. And then when I consider alpha beta, probably be better to write it out here. The first cycle that all these inputs are going to pass through is beta, because I got to read it right to left. So it's going to be passed through the cycle 1, 2, 3. And that's going to generate some outputs from each of those inputs. What would the next little mini cycle be that any of these inputs would get passed through when I'm considering the composition alpha beta?
6, 7.
Yeah, 6, 7. That's going to create some inputs or some new outputs. And then following that would be 2 and 4. And then 1 and 3. And just kind of how we set this up. Once I've been passed, my input and outputs have been passed through all of these cycles, kind of that last row is the final output we get for each corresponding input that we give in. And that's what's going to inform our new cycle, or how we can write our new cycle alpha beta. So now I just need to start tracking the changes. So if I pass 1 through the cycle 1, 2, 3, what is it going to become?
2.
Yep, 2. And then I pass 2 through the cycle 6, 7. What is that going to become?
2.
2. I pass 2 through the cycle 2, 4, and it becomes
4.
4.
Yeah. I had 3 people answer that one that time. Awesome. And the last one, because I know 4 is not in the cycle 1, 3, it just gets returns. So I can already go ahead and start writing out what happens. Alpha beta 1 gets sent to 4. And then I can just say, okay, well, let's just go through and track, see what happens to 4. Well, if I plug 4 into the cycle 1, 2, 3, what happens?
You get back 4.
Yeah, I get 4 back. Both of y'all got that. I pass it through the cycle 6, 7. It doesn't change it. It's going to stay 4. What happens when I pass it through the cycle 2, 4?
2.
Becomes 2. And then I pass 2 through the cycle 1, 3. It doesn't do anything. So 4 now becomes a 2.
Good question.
Mhm.
Why do you skip from 1 to 4?
Because my goal is to write out the cycle. So if I know 1 gets mapped to 4, then a question I can ask is then what does 4 get mapped to?
Okay.
If I wanted to do it just in table order, so go figure out what happens to 1, 2, 3, 4, 5, 6, and 7, I can do that. But then I have to go back and start pasting together this information that we're building as we go. So the initial process, kind of like we did on Wednesday, isn't bad. It's just not optimal.
Okay.
So now we got to figure out what happens to 2. I'm gonna kind of speed up because I think based on the answers, we'll do one more, and then after it, I'll kind of speed through and we'll kind of just fill in all the information to get it done with. But if I use 2 as my input and I pass it through the cycle 1, 2, 3, what does it become?
3.
3. I take 3, pass it through the cycle 6, 7. What does it become?
3.
Yep. Same thing happens for 2, 4. And then when I pass 3 through the cycle 1, 3, what does it become?
1.
1.
Oh, 1. So I know when I'm trying to write out this final cycle of alpha beta, what it looks like. Well, I know 1 maps to 4, 4 maps to 2, and 2 is going to map back to 1. So I'm going to have 1 cycle completed in this total product or composition. And then I'll need to go investigate some other numbers. So maybe what happens to 3, 5, 6, and 7. But does everyone see why so far we just kind of end with that cycle 1, 4, 2?
Yes.
Back around.
What was that, Xander? Sorry.
It moves back around, so the 2 will go to the 1.
Yep. Perfect. All right. Let's speed through the rest of these. Let's start with 3. Well, through the first cycle, 3 gets sent to 1. I don't see 1 appear in either of the next 2 cycles, so 1 stays 1. And then at the end, 3 gets mapped back to itself. So 3 gets mapped to 3. Let's go through 5. 5 is not in my first cycle I have in my list, so it doesn't change. Neither is it in the second, third, or fourth. So I end up seeing that 5 just stays as 5 throughout the entire cycle of this composition. What about 6 and 7? Well, 6 gets passed through the first cycle with nothing happening to it. It changes to a 7 when I pass it through that second cycle in our list. And then 7 persists through the rest of our cycles. And then we see similar story for 7. It passes through the first cycle I was about to say unmolested. It's technically true, but it's such a weird word to use. Unchanged. But then when I hit that second cycle, 7 turns into 6, and then 6 persists. So because 3 and 5 stay the same, there's no need to make note of that in my final answer of what the cycle should look like. And we see that the only things that do change left between 3, 5, 6, and 7, it's just 6 and 7, and they just keep alternating in between each other.
Question. So if we write 3 and 5, would that be considered an error, or we just don't need to write it?
You just don't need to write it. So the analogy, like I said on Wednesday, was it's like writing multiplication by 1, right?
Okay.
Technically, like writing that 5 just maps to itself and 3 maps to itself is acceptable, because, you know, if I would have said 1 times x is equal to 3, right? That's still, or I don't know, 3. Actually, I should say 3 times 1 is equal to 3. Why am I highlighting? It's like 1 times 3 is the same thing as 3. But we would say it's just kind of superfluous to actually leave that multiplication by 1 there.
Okay.
All right, what other questions y'all got for me, though?
One for me.
Cool. Yeah, if you don't have any, you can just give me a thumbs up. Forgot to say that. But thank you for speaking up, Xander. Awesome, Shanika's and I.
You asked if we have more questions?
Yeah. I did. But all good if you don't. Cool. Thank you. I'm just missing a thumbs up from Melissa. Let's assume she's writing vigorous. Oh, nope, there it is. Cool. All right, so one of the things you might notice when we start writing these cycles out, in some cases, when I can rewrite them, that's a terrible way to talk about that. Let me just give you the definition, because I only give you one true example. One thing that we always will like are what we call disjoint cycles. Disjoint cycles are just cycles that don't share any terms in common. So if we just let alpha have some numbers A1, A2, all the way to AN, and we let beta be a cycle with the numbers B1, B2, all the way to Bn, if AI is not equal to B sub j, oops, that should be an M, not an N for the B. So if A sub I is not equal to B sub j for any combination of indices I and j that you can think of, then we say these cycles, alpha and beta, are disjoint. Essentially, they don't share anything in common, any things they permutate. Only beta does it and alpha doesn't, or only alpha permutates it and beta doesn't. In fact, what we just wrote, that last cycle, which is a product of two cycles, 142 and 67, are disjoint cycles. So if I go through and I look at all the numbers in each of them, I see that they don't share any numbers in common. The numbers 6 and 7 do not appear anywhere in that first permutation, 142, and 1, 4, and 2 don't show up in the second permutation, 6, 7. And there are plenty of non-examples. We've also gone through a couple. So 1, 3, 5, 7, and 2, 3, 4, 6 are not disjoint. And why is that the case?
Because 3 is in both of them.
Because both of these cycles do something with at least 3. And they also have 2 different things that they do to 3. But that's not really the point. It's just more so that both of them affect the value 3. They permutate the value 3. So why do we care about recognizing disjoint cycles versus cycles that aren't disjoint? Well, it's because if I can recognize I have disjoint cycles, there's this very nice property that we always wish we have in groups that we can actually, we're not always guaranteed, but we can get it with inside these symmetric groups as long as we know that these 2 cycles or that any 2 cycles are disjoint. Anyone happen to know what that property is? What's the one thing I got a couple of y'all on your midterm? or homework that you want to be a property of a group, but isn't necessarily a property of a group?
Are you talking about subgroups?
No, not subgroups, but that's not a bad guess. What are you going to say, Shanika?
Does it have anything to do with that one step? Subgroup is a subtest?
Good
No.
guess. No. But good guess based on the question I posed. So what are the 4 properties or 3 properties of being a group? Unless, Melissa, do you think you have the answer?
And like you say, like A inverse times B inverse, that's not enough?
So no, that is not enough to show something as a subgroup. Because that property
Identity element?
close. All right, so let's go through. Yeah, let's go through our list of properties for a group. We had 3 main ones, right? So you had identity element was one of them. What are the other 2? Yeah, associativity, and then the last one.
Inverse?
Yes, everything has an inverse. So those are only 3 things we need to show that a set with an operation is a group. And then what is another property we can tack on? It's no longer just a group. It's a special kind of group, and it's a property that we always wish we had.
Abelian?
Yeah, so that's right, Chris. Abelian groups have this, and like Shanika said, sorry, Melissa, if you said something, I didn't hear it, but commutativity. So that property that it doesn't matter what order I operate things in, because we're so used to that with the real numbers and our algebra, right? Commutativity is always a given, but when we go to groups, it's never a given unless you can prove that the group that you're working in is abelian. But then we saw even in some groups that there are elements that do commute, right? We had the centralizers, we had the center of a group. And it turns out even when it goes to symmetric group or these permutation groups, my apologies, we can still even identify specific cases where certain elements will still commute. And that leads into this next theorem, which just says let alpha and beta be disjoint cycles in Sn. And if those 2 cycles are disjoint, then they commute. It does not matter which cycle I write first, the outcomes will always be the same. We can kind of see this with a quick example. Let's say that these are my 2 cycles. I guess to maybe match up with the notation, let's let alpha be that and beta be what, 2, 5. So what am I working in here? What do I assume? What's permutation group am I working in?
S5.
S5. So now I really only have 5 elements to work with that I can permutate. But if I look at alpha beta, so composing this 2 cycles in the following way, it'll be 1, 3, 4, and 5. So if I pass 1 through this new composition, I'm going to underline green for just to say first cycle, and I'll say yellow for second cycle. Does that, or I guess green will probably be better. So that green cycle, that cycle I just underlined in green, will that do anything to the value 1?
No.
No.
Right? 1 just gets passed through the green cycle, gets sent on to the yellow cycle, and the yellow cycle will do something with it, right? What would be alpha beta of 1?
3.
Yeah, it'll turn it to 3. What happens if I flip the order of the permutation? So now do B composed with alpha. Well, notice still, even if I just kind of keep this as yellow cycle and green cycle for ease of communication, right? The only cycle that's going to be affect the value 1 is the first one, the yellow cycle, right? And it turns it into 3, but does 3 show up in the green cycle at all? Or does the green cycle permutate the value 3?
No.
Yeah, right? The green cycle only does things with the value 2 and the value 5. So I can see anything that comes out of that the yellow cycle there, will never be affected by the green cycle, because any output that I can get from the first cycle, which is just 1, 3, or 5, anything that changes, will also be changed later on by the green cycle to 5. And I can flip my perspective around as well and say, okay, well, if 2, 5 is the first cycle to act, right, it's only going to do things with 2 and 5, and then whatever gets passed on, 1, 3, the cycle 1, 3, and 4 doesn't care whether or not you give it a 2 or a 5. It just stays a 2 or a 5. So we can even kind of see it in action just with specific examples, that as long as these cycles don't share any elements in their permutations, then it doesn't matter what order I write these cycles in. So before we get into the proof, if you have any questions for me, feel free to go ahead and unmute and ask. Otherwise, shoot me a thumbs up so I know we can move on to the proof. Cool. So to do this proof, we're going to let alpha and beta be disjoint cycles in some permutation group. And I don't know what the highest element is. This might be, I'm just going to write it in green for example of how I have to still be careful with this generalization. So the cycle alpha could technically be just the cycle 1, 3, but working inside the permutation group S200, right? So there might be a lot of elements outside of these just general permutations that exist inside this permutation group that aren't affected by alpha or aren't affected by beta. But there's also got to be some, because I know 1 will be affected, 3 will be affected. So there's at least some elements within S200 that will be changed by alpha. So we can structure our argument in the following way. So say alpha takes just some amount of elements from Sn. And it's going to say it's A1 through AM. I don't really know how many that is, but there's a slight understanding that M has got to be less than or equal to N. And I'd make a similar argument for beta. It's going to have some entries in there, not necessarily the same number as my cycle alpha, but there's some things in there. And all of these numbers, these A's and these B's, are inside my symmetric group. So we can actually say, without loss of generality, let my symmetric group be redefined in kind of 3 different parts. I can consider it as all the things that that first permutation alpha actually permutates or has an effect on. Everything that B permutates or has an effect on. And because alpha and beta are disjoint, I know all these A's and B's can't be the same. And then what's the third possibility?
There are other stuff inside of it that aren't in alpha and beta.
Yeah, exactly. And I'm just going to call those my C's. And then, I don't know, we'll do CK. I don't know how many those are, but I know I can break down my symmetric group SN into kind of these little three little subsets. And that will cover everything inside of SN. Now, here's the tricky thing. I'm trying to show that these two cycles commute, but these cycles are still permutations, and permutations are bijective functions. So, side question. How do you prove two functions are equal?
Assume that there's two of them.
Okay, so let's say F and G. Let me erase that D. That's even going to annoy me. Ah, there we go. So if we have two functions, we know they're equal if what?
Oh, does it have to do with the identity element?
Uh, it's kind of wrapped in there. And I remember there's things that you can do in linear algebra with linear transformations where it matters what the identity element gets mapped to. So it's not a bad guess, but that's not what I'm looking for. This is actually like an old algebra definition. I'm trying to just see if someone remembers, but I do love that guess. I can declare two functions equal if their outputs are always the same. Two functions f and g are equal if f of x is equal to g of x for all possible x in the domain. When you do this on the set of real numbers, it's kind of intuitive, right? For example, x squared is not equal to x cubed because I can find an input where I get two different values for the output. Like 2, for example. 2 squared is not the same thing as 3 squared. So x squared is not the same function as x cubed. But that's that nice little reminder that to prove two functions are equal, or maybe you're learning it for the first time, which I'm sorry if that's the case. To prove two functions are equal, you just have to show that for every input, the outputs are the same. So when I'm going through and I want to show that alpha beta is the same thing as beta alpha, then we need to show that alpha beta of some input is the same thing as beta alpha of that same input. For every element in my group. Or sorry, for every element in Sn. Actually, that's bad notation. Can anyone answer? This will be a fun little pop quiz. Why is it bad to say for all X inputs in Sn?
Because there could be more than this X inputs.
Ooh, good answer, but no. I'm sorry, Melissa, I wasn't able to understand that. It's a Zoom issue, not a you. It's a little better. I'm sorry, Melissa. I can't. So how about I save us? Yeah, sorry. I'm having difficulty. But let's go back to how we define Sn. Binding cycles. Where's my... Oops, did I go too far? Yeah, I went too far. What is Sn?
A symmetric group of degree n.
Mm-hmm. That's what we call it. So that's another way to say it versus just saying Sn. But what does it consist of?
You mean like the factorial stuff?
Factorial
Like the
stuff,
order?
essentially just the part of the sentence before what you read off to me.
The set of all permutations?
Yeah, so Sn is the set of permutations on a set with n elements, right? And when I go back to my proof, that means what am I passing through to these inputs or as inputs to these permutations? I'm not passing other permutations. I'm passing numbers. Really, it's, I need to come back up here. Maybe this will help you if I rewrite this. Without loss of generality, let A the inputs that I can choose, the things that I am permutating for this symmetric group, or not symmetric group, for Sn, group of symmetries on NL, permutations on N elements. Ugh, I'm even getting tongue-tied now. So I'm probably just going to try to stick with Sn so I don't confuse you too much. Sn is the set of all permutations on a set with N elements. So in this case, the set of elements that I'm permutating is that set capital A. And what we said was because of how we know what elements are being permutated inside of this set, I can rewrite it, relabel it to where it was kind of those three little same sub pieces that we had before, right? So it's the set of, I can organize it to where it's everything that A permutates, everything that B permutates, and then everything that neither A or B permutate, which is where all those C's came from. So when I'm going down to this proof, and when I'm thinking about how am I going to prove that these two permutations are the same, It's the inputs that I'm choosing are coming from that set A, the set of numbers that I am permutating. Why did it zoom in? I don't know. And since I had to backtrack, I need to make sure that we are all on the same page. Permutations are acting on a set of finite elements. So they're functions that act upon a certain set. So I needed to go back and rewrite my proof so that it was clear what the set is these permutations are acting on. And I'm calling that the set A. That is where all of my inputs for the permutations are coming from. So don't lie to me here. But if you're following along now after that kind of revision, give me a thumbs up. If not, please ask questions. All right, good. Thank y'all. So if I need to make sure the outputs are always going to match up given any input, I can really split my arguments from here on out into 3 cases. So I can consider one of those A's as my input. And I chose M. So if I just take some general value in there, I can figure out what happens when I throw it through the 2 functions, alpha beta and beta alpha. So if I take this element AI, A sub I, and pass it through the permutation alpha, it's just going to turn it into the next item that is listed in that permutation, right? Just how, like we said, when we go inside of a cycle, we start reading it from left to right. 1 gets mapped to 3, 3 gets mapped to 4, unless I'm at the very end, and then 4 gets mapped back to 1. So as long as I'm choosing one of the elements that is listed in that cycle for alpha, it gets changed. And I know it's going to just move on to the next element that is listed in that permutation, which I called AI plus 1. And there's a small little caveat here. This is only going to be true for I equals 1 through M minus 1. I want to erase. And if I happen to be that last element that is in my permutation, then I know it gets mapped back to A1. But really the point is, if I'm choosing one of these A's, little a's, from my entire set of n numbers, then I know I'm just going to be staying as one of these A's. And if that's the case, if I take this and pass it through the composition alpha beta, I know this is function composition. So first I got to figure out what happens to this element little a sub I when it passes through the permutation beta. Well, what is it going to become? What is the output as I pass little a sub I through the permutation beta? Well, what do we know about those 2 cycles, alpha and beta? They are what?
Disjoint.
They're disjoint. So anything that alpha would act upon, does beta act upon it?
No.
No.
Right? And what I've done is I've set up this case to where I'm now passing through something that alpha would act upon through beta. That is that beta of a sub I. So then what would be the output from beta of a sub I?
A sub I?
A sub I. It wouldn't permutate it. It doesn't touch it because it's one of those little a's. And then what does alpha of a sub I become?
A sub I plus 1?
Yeah. That next thing. And then if I flip it around and do beta alpha of AI, so I look at the other function, my second function, consider it with that same general input. Well, this is going to be beta of alpha of AI, little a sub I. But we just said alpha of little a sub I becomes a sub I plus 1. And then what is beta of a sub I plus 1 going to be?
A sub I plus 1.
Yeah, just that same element. Well, hey, looky here. In general, I choose any of those a's, and I know the output is going to be the same for either of these two function compositions, whether or not I look at alpha beta or beta alpha. So definitely don't have enough time to finish up this proof, but we can at least outline the next two cases. And hopefully if I write it down here. So I need to make sure I consider all inputs that I could possibly get from that set A. And now I've already covered the case where I choose one of the elements that is listed in the permutation alpha. What would be a next choice to choose so I can start covering even more of the elements inside my domain or the set A?
You can repeat that question, please?
So I need to cover all elements in the set A.
A sub n?
Well, technically, the way I have it written, you'd want to show it with a sub n, but you would have alpha beta of a sub m would be equal to alpha of a sub m, which would be a1, and beta alpha of a sub m would be beta of a1, which would be a1. So what we've said here is if I've gone through and selected any of the little a's or any of those elements which I've labeled little a from my set of numbers that I'm permutating, which we called capital A, I know the outputs for these two functions are going to be the same. I've gone through and said, all of these are good. What else do I need to check?
B sub I.
Yeah, I need to check to see, make sure that those two functions are going to have the same output for all the B's. And then what else?
The C's.
Yeah, and then everything that they don't share. And I got to make sure that the outputs are always the same. So that's how our second and third cases get split up. The first case was choosing the little a's. Second case would be to consider all my little b's. And that one went to n. And then the third case would be to consider all those c's. And as long as I can show that these two functions, alpha beta and beta alpha, have the same input for any of the inputs that I can choose in these last two cases, I've covered everything in the domain. I've covered all possible inputs. And if I can show that the outputs are the same for all possible inputs, then I know those two functions are the same. That's the story we'll finish up on Monday. But hopefully you can see how it plays out. I'll give you a hint. What we're going to write is pretty much the same as what we wrote in the first case. Just slightly different logic applied to it. But I will end there. It's a Friday. I know y'all ready to get out of here. So if you have questions for me about anything, this stuff I talked about at the end of class on Wednesday, etc., feel free to stick around and ask. Otherwise, get on out of here, and I will, or shoot me a thumbs up too if you don't mind. But get on out of here, and I will see you in person on Monday.
Okay, have a good one.
Thank you, you too.